answers to the Maple handout that most of you have, and I have one for you if you don't. It's the Maple that on the front page, it says Thomas 12th edition, section 15.5, and as I was saying, I think yesterday, the last three sheets of paper go with 15.7. So see if you can find that, and if you cannot, I can give you another one. And if you can find it, then go to the third sheet in from the back where it says Thomas 15.7 cylindrical coordinates problem 4. And then we'll start there.
Thomas 15.7.
Yeah, and which is this section, and then it says cylindrical coordinates, and then it says problem 4. It's the third sheet of paper back from the back.
Oh, okay. Oh, from the back.
From the back and
Oh,
down to the
okay.
third sheet, and it's on the back side of the third sheet of paper.
Okay. All right, got it.
So, save some time. Okay. So, we talked about this a week or so ago, the formula for the differential volume in triple integrals, if it's Cartesian, is dx, dy, dz in one of the 6 possible orders. And that becomes dz, r, dr, d theta in some order if you're in cylindrical coordinates, and becomes rho square sine phi, d rho, d phi, d theta. So notice there is the extra factor here of r and here of rho square sine phi, and that has to do with coordinate transformations, which we'll start to talk about at the end of today's class over in here and continue with in chapter 16. If you remember when we were talking about the differential volume in cylindrical and spherical coordinates, I gave you this handout. You remember that with the drawing of the box in cylindrical coordinates and the one in spherical coordinates. So that's one way you can see that these are reasonable. Second, Jay. So, if you can find then the maple that goes with the section 15.7, it's the back. Be sure you get this because I'm working with it. Problem 4 then, if you notice on the maple, all that I did with it was to enter it as triple int and get to the answer over here. If you're going through it, this one is cylindrical coordinates, of course, and the book has it set up. So in their setup, you see they have z going from minus root 4 minus r squared to 3 times it, and so on. So you integrate with respect to z, and you get the z square over 2 between these limits. And so then the 1/2, the 2 here is the 1/2, I'm squaring this, so I have the 9 and the 4 minus r square, minus I take away this one square, which is 4 minus r square. So there's 9 of them minus 1, so there's 8 of them. Half of 8 is this 4 that's here. So I finally have 4, and the integral 0 to pi and 0 to theta over pi, 4 minus r squared. And then you can multiply by the r, which I have here, and then I still ought to have written the integral there. I have a missing integral because I haven't integrated yet. So. Okay, like that. So now I'm integrating this, so I get the 4r squared over 2 minus r fourth over 4 between my limits, and put in the limits, and that gets me to this, and then I'm doing this integral, 0 to pi, and the 4 is still out here, and so then I'm going from here up to there. Notice that pi square is a common factor in the denominator, so I took it out, and it left the 0 to pi, and then I have the 2 theta square from that term, and the theta fourth, and the 4 pi square, because I took a pi square out in front over here. So then I integrate this to the theta cubed over 3, and then theta fifth, and 5 fours are the 20, and put in my limit. So I have this, and then I can reduce the powers of pi here, and then factor a pi cubed out. So I have 4 pi cubed over this pi square, and that leaves me 2/3 minus a 20th, and goes to that. And you see, if you do it with the maple, problem 4, I simply did triple in, first with the capital T, so line 13 is the integral that you see in the book or on the board, and then say value, and I get the 37 over 15 pi. See, so that's why this is Maple Appreciation Day, because as far as take a problem like this and get to here, you can't beat Maple or something like it. There's no doubt about that, but a person should go through it once in a while, or else you forget how, like so many things. Okay. Now, number 11 and number 31 are not part of what I listed in the homework, but we can learn quite a bit from them. They deal with the same volume, and what they're getting at is working out the volume in cylindrical coordinates and then working out the volume in spherical coordinates, or in a mix where you could use one system for part of it and one for another. So the picture that goes with both of these is what I've drawn here. You have a dome, which is part of a sphere. It's, you see, in Cartesian form, you have this. So in spherical coordinates, that's radius rho from the center here equals 2. And then So you come on your outer surface from the North Pole, you come down to what would be 60 degrees north latitude. It turns out that this, called the co-latitude, is 30 degrees. We'll see that eventually. And then you don't have sphere anymore for your outside surface. You have this cylinder where I'm showing, or trying to show, the outside wall of the cylinder in the green. And so what you're doing is you're down here and then you're just falling straight down, you see, on the outside that's cylindrical. So you could certainly build something like that that's a cylinder and then a domed top sort of thing. So the question is, what's the volume? And so if you're thinking of cylindrical coordinates, then your spherical dome, see your spherical dome, for example, is this in Cartesian form. Well, x squared plus y squared is always r squared, where this would be the r of cylindrical coordinates. So your blue up here from this would be the same as r squared plus z squared equals 4. And so you can solve for z, and you're talking positive z, so positive square root 4 minus r squared. So if you were writing a vector, as you would for maple, if you're getting maple to draw the picture, which of course I have there before you, your parameterization, which is what you mean when you write a vector with one or more variables that are to produce your curve or your surface. If you have just one variable like t, that's a curve, that's space curve, okay, like chapter 13 and the lines in chapter 12. If you have two parameters, you produce a surface, or at least your computer does. And so I'm producing this in cylindrical, using the cylindrical variables. R is the R out, and I'm using t instead of theta, so that with the maple I don't have, the system that I have is older maple, and I don't have the palette where I could go get the little Greek letter. I don't know if you saw the article in yesterday's Wall Street Journal, but apparently Apple is about a year away now on the Mac from having a system where you can make the keyboard any symbols you want. In other words, they don't have to be Roman letters, for example, for people who want to use, well, like Russian, Cyrillic letters, or of course the Far East, and also you'd be able then to do the math symbols. So this is not that far away. Anyway, meanwhile, being the age I am, I'll use the T. Okay, we're looking at the maple. It starts with the 15.5, and we're on the back end of it. So this will produce that part of the graph. If you look at my maple, you see what I've done with problem 11. I've typed display because I'm using more than one plot structure. And then you see plot 3D, and you see RT and square root of 4 minus R squared. And if you're in cylindrical or spherical coordinates, you have to say, because even though the r and the theta are from cylindrical coordinates, your vector, as you set it up, this is still x and this is, it's still a Cartesian form vector. So you have to tell it that you don't mean that this is x and this is y and this is z. You mean that it's cylindrical coordinates. So that's important. If you don't type the chords equal cylindrical, you won't get the picture that you think you should get, which would be this dome. And then the next thing I want to do is to get this part. The sidewall, you see, is r equals 1. So in cylindrical coordinates, r is always 1, and then this is the angle, the theta, going 0 to 2 pi, and z is going from somewhere to somewhere. So I have to figure out the limits on z. So when r is 1 and you're out here on the green, you see what you want to find is where this red curve is, where the sidewall will meet the dome. And so see, if you were up on the dome back here, that's this, when r is 1, you see right here that your z is square root of 3. So I'm looking at this and I've repeated my writing here. So when r is 1 on the dome, so that's the red curve on its edge, I have 1 and then any angle and then the z, which is root 3. And so then if you wanted to know what this angle is for future reference, like problem 31, where you're going to work with spherical coordinates, you could get that now. Your angle phi is in here between the z-axis and this line that goes from the center out to the curve here where the cylinder sidewall meets the top. And so at this point your radius is 1 there and your height is root 3 here, and so the tangent of phi is opposite over adjacent, 1 over root 3, and so that's 30 degrees, so pi over 6. Okay, so now you see if you wanted to do your cylindrical coordinates, you can get the volume because your z is going from 0 in the plane, say, of the equator up to the Arctic, from the North Pole down to the 90 minus 30, so 60 degrees north latitude. So that's 4 minus r squared in cylindrical coordinates. And then the r is going from 0 to 1, and the angle around is 0 to 2 pi. And you could work this out by hand, or you can simply ask Maple. Look at my pictures. So first time, you see I did the display, I have the dome, and then the second one is the cylinder, which is the 1t and z. I've only drawn the first, well, from there to there. I only drew this part of it to see what was going on. So that's why my t goes 0 to pi over 2. You could draw 0 to 2 pi, but it would look the same because you can't really see it. And then I have the normal axes, the wire frame style, so you can see through and see the axes. So that's on the top of the next page. And then I did it over again, and I have the patch contour surface. And you can see in that view that I have only part of the figure. Again, because the T went only to pi. Well, let's see, I went 0 to pi that second time. So I have half of the figure. Okay, then I did triple int. Okay, so that's this. And then I did value, and that's this. And EVALF, you get the decimal, and you turn the page. And number 17, top of the page, is the number. And the R in the RDRD theta that we saw last week when we looked at the handout that has the boxes is, if you're thinking of it geometrically with the boxes, it's the height of the upper box, and it's a kind of scale factor between the polar or cylindrical coordinates and Cartesian coordinates. Is there anybody here who didn't get this from me when we were going through? I had the pictures over here on this board. It's about a week ago. If anybody needs these, I have them. Anybody need these? Okay. So then, if you went to problem 31 in this section, you would do this using spherical coordinates, or at least use spherical coordinates for the part where it's the most natural system, which would be the spherical part. You can do it either of two ways, which I have on the board here. You could do, you could divide your problem into the volume of the cone, which I'm trying to indicate with the red color. I'm trying to indicate the wall of the cone. Think of like an ice cream cone, except that this is a true cone in the sense it comes down to a point, whereas what you buy now as ice cream cones more often than not are more like a cup. But if it came to a point, it would be a cone. And then here's your scoop of blue colored ice cream that's up on the top, you see, like a scoop would be. Okay, so this we're thinking is part of the sphere, so you could at least use spherical coordinates for that volume. Then the other part would be the part that goes down to the base in the XY plane inside the cylinder. And if you're going vertically with Z values, you're going from 0 to the wall of the cone, which would be the red. So you could look at it that way, that you have the two volumes and you're adding them together. As I'll show you, you could do it first using cylindrical coordinates for this lower part, since this outside wall is cylindrical, and spherical coordinates for that. Or you can do it all spherical, in which case you have to figure out how to write the vertical line in spherical coordinates, which I'll show you. It's similar to what we faced when we were doing polar coordinates, double integrals and polar coordinates, and we had something like a triangle as our region, where we had to figure out how to write a horizontal line or a vertical line in polar coordinates. And if you remember, you use x is r cosine, so r would be whatever your x value is over cosine, so it would be secant. Okay, you got the same kind of thing here. You're going to be dealing with the secant of this if you're going to do it spherical. Okay, so I'm thinking in problem 31 of the sum of what I call cone with the red and dome. So dome is the first part where it's the contents of it's the volume of the ice cream cone that's packed tightly with this blue ice cream. Then dome is that volume. Then cone is what goes from the floor here in the XY plane up to the red. Okay. And so for the dome then, you see the rho, which is measured from the center, goes 0 to 2. If it's this in Cartesian coordinates, it's just simply rho from here out equals 2. And then the angles can vary as they do. So when you're using spherical coordinates, your scale factor or projection factor is the rho square sine phi, and then you have the d rho d phi d theta, and the rho is 0 to 2, the phi is 0 to pi over 6, as we pointed out, because this is 30 degrees there, and you're going clear around, okay? So you can do that one, which I have with the maple, if you will look. Let's see. I'm on the last sheet of paper, and I've it's below the second picture there. It says formula 20 below gives the conical volume with the sphere on top. So the triple int, the first one, I've used R now for rho, and I've used P for phi for the Greek letter. And the rho or the R is 0 to 2, and the angle phi is 0 to pi over 6, and then the T for theta is 0 to 2 pi. So 20 is my triple integral, which is this. And then I have value, which is line 21. Notice that value, that's not the same as this one, which was for the whole thing, done cylindrical coordinates, because we've only done part of it. And if you do the EVALF, you see, turn the page, you don't get the 5, you get 2.24. Again, because you have only this part. So now you're doing this part. So if you were going to do this part and use cylindrical coordinates, then you'd be doing things like here as far as the setup on the dz, rdr, dt. And the thing is, what are the limits on the z? Well, they start certainly at 0, but they don't go up to the dome now. They're just going to the red. Well, what's that? That's like a line that's at, well, it's at this 30-degree angle coming down, or 60-degree angle if you're going from the bottom up to it. And you see when this is 1 out, this is 2 up. So you have a line through the origin, specifically say this line goes through the origin, and the coordinates there are 1 over and 2 up. Well, you know how to write the equation of a line goes through the origin if you know another point on the line. And so that will give you, see, it's, well, this height then, see, it's 2 like that, it's 1 like that, and it's square root of 3 like that. So the slope of the line is square root of 3 over 1. The hypotenuse is the 2, if you think of a right triangle. So, you know, line through the origin, y equals mx, where m is the slope. It's that simple. So your slope is square root 3. So z is 0 to root 3 r, and then the r is 0 to 1, and so on. So you do that integral, and you get this. Then if you add this to this one, so you have 16/3 minus 8/3 root 3 plus 2/3 root 3, and then pi is the factor of everything. And minus 8/3 plus 2/3 would be minus 6/3, and that's 2. And that's what this says. So the two pieces add together, you see. So you can do them that way, or if you want to do this same thing out in here with spherical coordinates, you can do that. What you have to do is see that when r is 1, so that you're on this wall, r would be, see now, rho sine phi as 1, so the rho would be, see, this is your connection really between cylindrical and spherical coordinates. Rho is this, and r is this. And the r is the rho sine of the phi, which is here. See, because this is r up here. So this r is this rho sine of this phi. That's how to look at it. And so then the rho is the r, which in this case is 1 over sine phi, so it's cosecant. It so happens so that in this problem the r is equal to 1. It could have been something else, of course, in some other problem. So it's going to be whatever is your r over sine phi. Okay, so that means then your limit on rho is 0 to cosecant, which is 1 over sine. And then you have your angles. See, you're coming from pi over 6 down to pi over 2. So that's there, and then going clear around. Okay, so then if you do this integral, that would be the one, that would be the way I did it with the maple. If you look at the very last thing that you have there, triple N, remember I'm using the letter R for rho and I'm typing. So it's really like rho square sine phi, and then 0 to cosecant pi over 6 to pi over 2, and then 0 to 2 pi. So line 23 is the triple integral, which is this one. And then EVALF is 25, and if you add that to line 22, you'll get the same thing that this is. In other words, this one, if you take this is the exact value and add it to the one to this one, then you'll get that again. So you can do this problem really three ways. You can do it all cylindrical, you can do it all spherical, or you can do one part spherical and the other part cylindrical. And so I think anybody, by going through all this, I think this shows a little more of what's going on. Notice that the other thing that I have that we've kind of skipped over is over the other end of the board. See if I think I have problem 11. I guess I didn't. Oh, okay, yeah. On the next, line 18, as it's numbered, from 15.7, problem number 21, is a triple int with spherical coordinates, and you see Maple's answer is line 19 is pi squared. So if we go to the other end here, here's the problem 21, and so if you do this thing by hand, first of all do the row, so rho square d rho would be rho cubed over 3, and put in your limits 0 to 2 sine phi, so the 2 cubed gives you the 8/3, there's the 3, and then you have sine cubed phi and another sine, and d phi d theta. Remember this sine, the green one, is there, it's essentially the scale factor together with the rho square. Okay, so now you have to do sine fourth, so you have to write that as sine square times sine square. When you're doing powers of sine and cosine, the hardest problems are the ones where it's an even exponent, because then you can't slice off a cosine somehow to do a u substitution. So you have to do trig identities. You use that 2 sine square equals 1 minus cosine of twice the angle, and you do it twice, one for each sine square. And you also notice that 8/3 is 2/3, 2 and a 2. You need these 2's to rewrite this as 2/3, then 2 sine square, which is 1 minus cosine, 2 sine square again, which is another 1 minus cosine of twice the angle. And so this has replaced a 2 sine square, and this has replaced a 2 sine square out of the sine fourth. Maybe I should write that. Okay, now we're working on problem 21, which you can still find there in those notes. So then I FOIL this out and get to there. And now I have another square. So I use this identity that whatever the angle is, you see, with this identity, you're going to double it. So 2 cosine square of the 2 phi will become 1 plus cosine of 4 phi. You have to double the angle. And now I'm going to use this 2 to get the 2 cosine square. So I've taken this 2 in, so I have 2 and 4, and the 2 cosine square, 2 phi, which now becomes this. So then altogether, I have 1/3, and I have 2 and minus 4 cosine 2 phi, and 1 plus cosine 4 phi. And then this one, I can take a 2 from the 4 and put the other 2 with the d phi for cosine u d. And so finally, I get to here, and then I evaluate between 0 and pi, and sine of 2 pi and sine of 4 pi and sine of 0 are all 0. So I have 2 and 1 are 3 pi. So I have 1/3 the integral of 3 pi d theta, and that gets me the pi square. And that's why I said Maple Appreciation Day after I got done with all this. But it isn't a bad thing to do something this way once in a while, just to remember that you can. Okay. So now, preparing for chapter 16, let's look at the rest of what I have, for which there is a handout that you are about to get, which does not surprise anybody. It also won't surprise you if I give you this handout.
Thank you.
This projection idea that goes with the little set of notes here. Two of you. I have time. So the area then itself would be this magnitude. So I didn't write like that. And so if you think of some point up here on the surface at the intersection of 2 curves, say C1 and C2, like this, you remember that the partial derivative with x would be the slope of the tangent. This is like basically a special case of the directional derivative, like on your test. But if you're doing things in the direction of I, your directional derivative is just your partial with x, and so then it's the slope of the tangent as the directional derivative is. Or if in the direction of j, then your directional derivative would be the slope of the stick like this, and that would be your partial with y. So if you're looking at these vectors, T1 and T2, as T1 parallel to the XC plane and tangent to the curve C1, and T2 parallel to the YZ plane and tangent to curve C2, then because it's the partial derivative, because it's parallel to the XC plane, your f sub x is your slope at, say, there, of C1, and that's like dz dx. You could use the straight up and down d's because you're limiting yourself to a plane where it's parallel to the XC plane, so y is constant. So then their only variables are the z and the x. And in the same way, your f sub y would be the slope of C2 because now your x is constant. You could write it as dz dy. So then you could write your vector sum for the vectors T1 and T2. You see, this one has a 0 component in the y direction because it's in a plane parallel to the XC plane. And so you have dx coming toward me and dz going vertically. So dx 0, and then if your slope is dz dx, dz is f sub x dx. So I'm taking this times that for dz. And then I'm doing the same thing with this times f sub y for this dz in talking about getting that vector as a vector sum. So then I can rewrite my T1 and T2 in terms of dx, dy, and these partial derivatives. Remember, the dx and dy differentials would be the sides of the green tile, which would be the projection of this one down into the xy plane. See, what we're talking about here is getting what I've been calling a projection factor or scale factor between the size of a slanting tile up on the surface, which is the red, and its projection, which is the green tile on the floor, which I'm thinking is the XY plane, like the floor of the room here. So I have my T1 and T2, then I can do the cross product, which will get me the area of the red tile, and there'll be a sense of direction in the cross product, which would be the normal, that'd be the unit normal M. So your cross product then is actually a vector where your sense of direction is here and your magnitude is this ds, which is this magnitude like that. And so then let's see what you get if you do the cross product here of the T1 and the T2. So you notice that dx is a factor with the T1 and dy is a factor with the T2. So if you think of well, probably better to look at how I have written it on the paper. So I have my tile, and so then what I'm doing, I'm taking the 1, 0, and f sub x that I get here if I factor out the dx, and the 1, 0, 1 fy that I have here if I factor out the dy, and so I'm doing that cross product. So you see the setup here with the ijk, ij, the 1, 0 f sub x, and I repeat, 0.01 Fy, and I repeat, and I do this cross product, and I get this vector, minus Fx minus Fy and 1, which is also the gradient, back to chapter 14, of z minus f of xy, because that would be partial with respect to z would give you the 1, and then partial with x would give you the minus fx, partial with respect to y would give you the minus fy. So these things, I hope, are starting to come together, that what we talked about as the normal to a surface, which is the gradient, you can take the gradient of your expression for your surface written this way. You can think of the tiles and the cross product and get the same thing out of that. And then finally, if you think of your surface as parameterized, in the sense of, say, R is, this would be like with the maple, the vector. R of x and y is x, comma, y, as your two Cartesian variables, and then f of x, y is your surface, your z. If you write, in other words, if you do this, then your partial with x, you see, of a thing like this is going to give you 1, 0, and f sub x, and that's this line. And your partial with y is going to give you 0, 1, f sub y, and that's this line. So that's how I got these two lines saying that I'm doing this cross product. This is how, if you were doing maple to draw the surface, you'd get it to draw a surface if you're using x, y variables and know the formula for your surface in terms of x and y. That would be like what we've gone through today with the cylindrical and spherical coordinates, where I'd have either, well, with the pictures that were over there, either these were the cylindrical coordinates and then the function in terms of cylindrical coordinates, or the spherical ones. You do the same thing in any of the three coordinate systems, and then take your cross product, and what you get, a thing like this, which in this case is square root of 1 plus fx squared plus fy squared. That's what I'm talking about on the sheet here. That's the scale or projection ratio between the size of this tile up here and its shadow down here in the XY plane, its projection. In other words, what I'm saying here, the magnitude of that cross product, which is this in this example, or magnitude of this gradient, which is the same thing, will give you actually the secant of the angle between the normal to the slanting tile, so this angle is gamma in here between this red vector and K. So the secant of that angle is what this is giving you, and what we call the area cosine principle is the relationship between dA in green, which is dy dx, and this up here, which isn't just dy dx, it's this thing times dy dx. I've written that out on the back side of this sheet of paper if you want to look through that. So where we will pick up with this, where I have more room to go on through to do the back side, will be next week, of course. But try to go through this and see if you can figure out what's going on a little bit, and we can come back to it as we start chapter 16. Chapter 16 is the rest of the class, and so you can see by the amount of time I've allowed that I think it's the most interesting of the material, and that's a translation means that I think it's the hardest, obviously. And what a lot of it is about is this business of working in one coordinate system and then another and another, where you're kind of doing projections from one system to the next. And there's going to be a factor one way or another when you do that. So I guess we'll meet again Thursday. I guess there won't be any more of these football games before Thursday, where it'll keep everybody up all night wondering how are they going to get out of this one. It's amazing what they